Okay, allow me to share my screen. Please let me know if my slides are transitioning. If not, please inform me. Okay, so we are now on the topic of numerical integration. It's very easy actually. It's the way we determine the values of non-elementary integral using two approximation techniques. Okay, this is based on the fact that if we're going to draw the curve represented by the equation or by the function that appears in our integral, and that same function is actually referred to as the integrand. It's actually determining if you define that area, it's actually, if you define rather the answer to that integral, it is actually the area under the curve, bounded by the limits of the integral itself. Okay, so that's the purpose of this set of slides. So for our learning objectives, so at the end of the topic, you should be able to approximate. Take note, class, of the term approximate values of definite non-elementary integrals. Now, elementary integrals are those integrals which you have processed, evaluated last term, midterm. So you were given a lot of integration techniques on how to process those, shall I say, elementary integrals. They are indefinite in the sense that they don't have limits. Now, the primary application of the two approximation techniques mentioned here, the trapezoidal rule and the Simpsons rule, is on the determination of the value of the definite non-elementary integrals. So meaning, those integrals which could not be processed using the techniques that were covered can now be answered, evaluated using these approximating techniques or methods. Take note, class, it's just an approximating method. So meaning, it's not really the actual answer, but it can approximate the answer depending on the number of, shall I say, divisions on your particular area of the curve. Okay, I will explain as we go along. Okay. Now, what are examples of non-elementary integrals? Integrals that could not be processed using the techniques that were discussed to you just last term. So these are examples. So sine of x over x dx is a non-elementary integral just like cosine of x over x. Sine of x squared is also a non-elementary integral. E raised to x squared, e raised to negative x squared, they cannot be processed using the techniques that were taught to you. Same thing with the cosine of x squared. Now, e raised to x over x, e raised to minus x over x could not be processed using techniques previously discussed because they are non-elementary. And so on. So you have here x raised to x. So the base this time is another variable raised to another variable. So this is non-elementary. So these are actually non-elementary. The examples you're seeing here are non-elementary indefinite integrals because they don't have limits. Once you place limits to this, they become non-elementary definite integrals. The slides are not moving. Okay, let me just close this one. So these are our learning objectives. Okay, sorry about that. The slides are not transitioning. So I would like to share to you these examples of non-elementary indefinite integrals. I have enumerated them a while ago. They are indefinite because they don't have the limits. They are non-elementary because they cannot be processed using the techniques covered just last term. Okay? Then once we place limits already on these integrals, they become definite non-elementary integrals. And the methods that will be discussed in a little while approximates the value, the actual value of this definite non-elementary integrals. So we name this topic numerical integration, a process of approximating the value of non-elementary definite integrals. So we have two methods here. We have the trapezoidal rule and Simpsons rule. Now, from the term trapezoidal rule, I mentioned a while ago that if, let's say, you're given a function that needs to be evaluated, the function that is referred to as the integrand, you're given integral. This is, let's say, the graph of your function, the one in blue ink, and it's bounded by the limits of integration a to b. So this a and b are actually values of x because we are integrating in terms of x. So this curve, this area under the curve is bounded by these regions f of f sub a and f sub b. A is the lower limit of integration and b is the upper limit of integration. We are interested, class, in this region. So the area, actually, we are interested on the area of this region, this one. The entire thing, we're interested with the area of this entire thing. But it has to be only on the area or the region bounded by A and B. So this part here is not included anymore. So in terms of using the trapezoidal rule and finding the area under this curve, it only approximates the value of the area. So instead of giving us the answer, which is this exact thing here, so this is your curve and these are the lines bounding your curve, including the x-axis here, it will only solve or only give you the area of this trapezoid. We know what a trapezoid is. It's a polygon which has a pair of parallel sides. So these are the parallel sides of our polygon. Now, in your geometry, plane geometry, we use the symbols to denote that these sides are said to be parallel to each other. Of course, this side and this side are not anymore. So since trapezoidal rule only approximates the area under the curve f, this is our function f, so it's only actually determining this area, this one, only under the trapezoid. So that is why we say it's just an approximation technique. This part here is not anymore calculated. That is why we call it trapezoidal rule. Now, how do we use trapezoidal rule in approximating the area under this curve bounded by these two vertical lines representing the limits of integration a to b? So of course it has a formula, and that's the thing that I'm going to show to you. So from this very simple illustration, class, you would know now, you have an idea, because our next topic would be the same topic here, areas under the curve, that when we are determining the value of a definite integral, we are actually determining the area of the curve or under the curve bounded by the limits of integration. So in this case, you are determining the area that I have placed the orange slanting line originally. Now, question, how do we determine the area using trapezoidal rule? So I have drawn here already the trapezoid. So clear my markings here, and let's see how it's going to be determined. So the function f, this f here is your integrand, will be approximated to the function of f sub p. What is f sub p? This is your f sub p. Okay? The vertical slant, no, not vertical, this slanting line here. The original function is this one, the curve. And it's bounded here by these two red lines, vertical red lines. Now, what we do, we approximate the value by only accounting for this area, the area of the trapezoid. Okay, so that's what is done here. Congruence meaning it's more or less the same as. So the value of the integral of the function f is more or less the same as the value of the integral of the function f sub p, where f sub p is a linear polynomial interpolation that is, so this is your f sub p. Now x minus b all over a minus b times the function of a, or that is the value of the function if a is substituted to the variable. Then you have x minus a over b minus a times the function of f of b. Now, if this particular expression class is likened to a formula determining the area of a trapezoid, so what's a trapezoid? I'd like to draw a trapezoid. This is your trapezoid. Yeah, just make it look similar to the one that was drawn previous slide. So the area of this trapezoid is actually the average of the lengths of the parallel sides. So let's say this is A and this is B. This is H. So average, you take the sum and you divide by 2 and you multiply it with the height of this given trapezoid. So in that sense, we apply this formula of the area of the trapezoid to the function of P, which is also the trapezoid that approximates the value of the area under the curve. So you can see you have H over 2 times the sum of f of A plus f of B, where H is just the difference between B and A. Like, take note of this. So if you have a piece of paper there, you write it down. H, the height of the trapezoid, is B minus A. And you have the area of the trapezoid, which is the area of the function f sub p, which is more or less an approximation of the real area of the function f. Okay? Now, write it down because I'm going to go back to the figure and show to you why is that so, using the formula that we have here. Okay? I clear my markings and we'll go back to the previous slide. So you could see here that this is your, like this. This is your f of A. This is your f of A. The function value when x is equal to A is f of A. Your f of B is this, the function value when x is equal to B. Now notice that this f of A and this f of B are actually the A and the B that I wrote in my illustration of the trapezoid. The only difference is this trapezoid has the height represented by this one. Now what is this height? If you're going to get the value of this height using the coordinates that we have here, that would be B. From 0 until here is B minus A. That would be the height. So that is why you get to see a formula of B minus A for the height. So B minus A times the quantity f of A plus f of B divided by 2. Because in terms of the area of the trapezoid, you have the height times the average of the sum, rather the average of the lengths of the two parallel sides. So this is our original formula. If we're going to apply it in here in our illustration, you will have the height, still height, and this A and B are f of A and f of B. So it's written there as f of A plus f of B. You have the 2 there divided by 2, it's written here. So the area of this curve bounded by these two vertical lines was approximated using the area of this trapezoid. And this is the area of the trapezoid now. Okay? Now, I'll clear my markings and we'll proceed to the next slide. So you could see now that the formula for the area of the function, or that's the value of the non-elementary integral, is using the area of that trapezoid. The trapezoid that is in the area under the curve bounded by the two lines representing the limits of your integral. So you can see now that this is the formula. Okay, that's for trapezoidal rule. Now, that's only on the note that you're only using one trapezoid. So this is for one trapezoid. What about if you have two trapezoids? So in the same area that we're talking about, you divide it now into two parts, of course, with two trapezoids in it. This is your first trapezoid, and this is your second trapezoid. Okay? This is still your lower limit. This is still your upper limit, and this is the middle value between your lower limit and your upper limit, and that is your x sub 1. Now, in here, we approximate the area under the blue curve bounded by this line x sub 0 and x sub 2 using now not just the area of one trapezoid but two trapezoids. If you notice, if you're going to compare it here, you see this big area that is left out, where this one in here, the area is just smaller. So the more trapezoids you use, the more trapezoids you have in here produced by dividing the area under the function, the more accurate is your approximation. So you have here two. So the left out area in the approximation process is smaller than the previous one, which happened when you only have one trapezoid. So this is now what you have. Now, what would be the corresponding area? So, of course, the area now will be the sum of the two areas of the trapezoid, not just one trapezoid, but two trapezoids. So, you can see now in here, this is one area for the first trapezoid. This is another area for the second trapezoid. Okay, f sub 0, rather f of x sub 0 plus f of x sub 1. Where is that? This is your f of x sub 0. This is your f of x sub 1. So these are your two parallel lines which you added and divided by 2. The height would be this height, only this height. So x sub 1 minus x sub 0. That would be the height for the first trapezoid. The second trapezoid will have a different height. That would be height rather. That would be x sub 2 minus x sub 1 because this would be now its height. As to the average of the lengths of the parallel side, it would be now the f of x sub 1 and the f of x sub 2 added divided by 2. Now, you could see that you have now this. The area of the two trapezoids. If you're going to simplify our equation here, since you have f of x sub 1 here and you have f of x sub 1 here, we might as well add. So you have 2 f of x sub 1. You have f of x sub 2 and you have the f of x sub 0. And here you have the h. This time, the h that you have in here, since you have already factored out this 2h here, same thing with the 1/2, is now the difference between x sub 2 minus x sub 0. Because anyway, if you have two trapezoids, these two height, if you add these two height, that would be just the difference of x sub 2 minus x sub 0. That's what happened here. Okay, this is now your formula. Now, let's proceed. So you would see. What about if you have 3? So if you have a smaller left out area for two trapezoid approximation, for 3, it's even smaller. So you have now 3 areas of trapezoid to take the sum of. So we have to see now, you have 3. So you have, since you have 3, if you're going to simplify, take note, you will have now f of x sub 0 plus twice of f of x sub 1 plus twice of f of x sub 2 plus f of x sub 3. This h now will be, take note, h sub 3 minus x sub 0 divided by 3. If you had only 2 class, I'll go back to 2. If you only have this 2, x sub 2 minus x sub 0, this is the entire height. You divide it by 2, that would be the height of these two trapezoid. As you can see here in the formula, x sub 2 minus x sub 0 divided by 2. If it's 3, like this one, the same thing, x sub 3 minus x sub 0 that would be this, right? If you divide it by 3, that would be the individual heights of these trapezoids or trapezoidal part. So you have now h is equal to x sub 3 minus x sub 0 divided by 3. Thus, for any n intervals, you will make it more general depending on your comfort zone. You want it to be more accurate. So we say you choose bigger number of n. So if for n intervals, this would be now the general formula for trapezoidal rule. Okay, the general formula for trapezoidal rule. Now, what do you have in here? What's the very important thing that you should only understand about this formula, because there's no point that you should memorize? The first term is always the f of x sub 0. The f of x sub 0 is just the value of your function substituting the lower limit of the integral. Okay? The f of x sub n is the value of your function. This function, I'm referring to this function, when you substitute the upper limit of your integral. Okay? Now, in the middle, you will have the terms multiplied by 2. So you will have 2f of x sub 1, 2 of f of x sub 2, x sub 3, x sub 4, until you reach that f of x sub n minus 1. If n is 10, then you will have 2f of x sub 9 as the second to the last term, because your n is 10, meaning you had 10 divisions in your area under the function of the curve of your function. Your h, the h that you see here, is now the same principle as applied with the other areas divided by n trapezoidal parts, is x sub n, the farthest or the upper limit, minus the x sub o, the lower limit, divided by the number of division. This is also representing the increments to which you're going to substitute the value of on your function. Anyway, I will explain with a specific example in a little while. What is important is you get to see the formula. It's just all about the formula and understanding the things that should be substituted, or the variables that needs to be substituted to your formula. Okay, this is for trapezoidal rule. Now, we go to, let's say if I have already the example. So I'll just clear my markings. Now you have sine of x dx integrated from 0 to pi. Okay, it's 0 to pi. Class, you may say, Miss Ali, you said we're going to approximate the value of a non-elementary integral. Now, the example that I'm giving you is an elementary integral. It is not non-elementary. It is elementary. I just chose this for illustration purposes. So there's no point of you having to approximate the value of this elementary integral when, of course, you know how to evaluate this using the techniques of integration that you have learned. This is just for illustration purposes. The trapezoidal rule and the Simpsons rule is applicable to non-elementary definite integrals, meaning, class, expect a function value here or an integrand value here, representation here, which is complex, not as simple as sine of x. As I've said, this was just chosen so that we can illustrate to you, or I can illustrate to you, the process of determining the value using trapezoidal rule. So in this example, you will evaluate the value of this integral. Rather, you will determine the value of this definite integral using, for the first case, 6 subintervals, and for the second case, you will use 12 subintervals. Okay, and compare which of the two, of course, will have a more accurate answer. Now, notice here that your A is 0, the lower limit of the integral, and your B is pi, the upper limit. Okay? Your integrand or your function is the sine of x. Okay? That's your sine of x. Now, since in the first case, number 1, you have n intervals, you will divide into not equal, but you will divide your area under the curve of sine x using 6 trapezoidal parts. So they are not equal. I will not say equal because of course they are not equal. 6 trapezoidal parts. So then the h that should appear in the formula that I have shown to you a while ago will be b minus a divided by n. So that would be pi minus 0 divided by 6. So that would be pi over 6. And this is the increment that you will add starting from the lower limit until you reach the upper limit. What do I mean by that? For the first lower limit, this is division 0. Your x would be, of course, 0, the lower limit. The next would be for your next value, for your f of x sub 1, from the 0 here, x sub I, you will add pi over 6. And this pi over 6, you will take the sign of. The sign of pi over 6. By the way, your calculators should be in radian ohm. Okay, this is your sign of pi over 6, whatever the value of that. For the next, you're going to add to pi over 6 another pi over 6, and that would be 2 pi over 6, or that would be pi over 3. Take the sign of that. You do the same. From 2 pi over 6, you add another pi over 6, that would be 3 pi over 6, and that would be pi over 2. This one would be 4 pi over 6. This one would be 5 pi over 6 plus pi over 6. That would be 6 pi over 6, or that would be your pi. You stop now because you have already reached the nth value. And now you have reached as well the upper limit, which is pi. You will know you're doing the right thing if the value of x that you have reached until the nth interval will be equal to your upper limit of integration. And this is actually pi. Okay? So this is now your function values. What would you do with these function values? You substitute it on the formula. What is our formula? F of 0. So you take the value of sine of 0. That will be 0. Then the middle values here, you notice you have 2, 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 until f sub 5, until this one. Your f sub 5 is the sine of 5 pi over 6. So you're going to place the values there of the answer of this, whatever are the answers. Your f sub 6, which is your last function, would be now not needing the multiplier 2, just like your first term. So wala siya yung multiplier na 2. Okay? You add all of this, you multiply it to h divided by 2, where h is like this. Pi over 6 divided by 2, or that would be pi over 12. Your answer will be this one. Can you do that, please? I'll give you 5 minutes. Anyway, you have it here already. Check if you can get the value of 1.9540. Never mind the next values here. So limit your decimal places up to 4 only. I'll give you 5 minutes to do that. So you have now 1.954 for the approximated area using 6 trapezoidal divisions for the area under the curve sine of x bounded by the line x equal to 0 to x equal to pi. Now question, how was this error arrived at? So the error class is simply the actual value minus the approximate value divided by the actual value. So how do you get the actual value of the integral of sine of x from 0 to pi? So it's very easy actually. All you have to do is use your calculator. You have the integral function there in your calculator. So place in there sine of x with the limit 0 to pi. So let's say, for example, if this is integrated actually, this would be, the sine of x would be negative cosine of x from 0 to pi. Right? And right? Then you substitute. So you have negative upper limit first, cosine of pi minus cosine of 0. Now you have here the negative of the cosine of pi is negative 1, right? And the cosine of 0 is 1. So this is negative 2 and your answer is actually 2. Plus this is the actual correct value, okay, for this integral. So how do we know, how do we get the error? So it's the absolute value. So error, I'll just place in here. The error is the absolute value of the difference. So absolute meaning it's not important whether the difference is positive or negative. So I'll copy this one. You divide it by the actual. Okay, times 100. The error that you'll be getting is this error that you have here. It's 2.29 or 2.30%. So that's how much this approximating process deviates from the actual value, which is 2. Do you get it? Any questions? Okay, so there aren't any questions. Now I've cleared my markings. So that's how you determine the error and determine the area using 6 sub-intervals. We will be repeating the same procedure class using 12. So if you're going to use 12, your b minus a would still be pi, but your n this time is 12. Now, so meaning you're going to increment the x value here by, not by pi over 6, but pi over 12. You're still going to start with 0. Then you have pi over 12. You add pi over 12 to that, so you have 2 pi over 12. You add another pi over 12 to that, you have 3 pi over 12. You're going to do that until you reach the 12th division. So you will have 12 pi over 12, or that will be pi. And this pi is actually your upper limit. These x values, you're going to substitute to the sine function. Okay? And then just like what we did a while ago with using the 6 intervals, this time, going to use 12 intervals. So you have f sub 0 and f sub 12 not being multiplied by 2. All the terms in between will be multiplied by 2. The h that you have here will be pi over 12. And you're going to divide it by 2. So that's actually pi over 24. The answer is 1.989 if we're going to round off to the nearest third decimal places. So you have 1.989. If you're going to compare it with the previous, this is only 1.954. The other one is 89. So this is more accurate because this is nearer to. So look at the error now. The error is just 0.5718. This tells you that the more divisions, the more areas under the curve that you need to approximate the value of, the more accurate is your answer. The same principle, the same concept is also true whether we're talking about Simpsons rule. This one is trapezoidal rule. We're approximating the area of the function, the curve of the function, using the areas of the trapezoids, the trapezoidal divisions that you used. Okay? So very easy, not so difficult. So you're going to make class this, shall I say, table. That way it would be easy for you to account or calculate the answer using this approximation techniques. Now we go to Simpsons rule. Now, if trapezoidal rule approximates by, so let me annotate, approximates by making it a trapezoid like this. Muna si trapezoidal rule. It's a trapezoid. You have a straight line here connecting the ends. Simpsons rule is that of a curve. It's not using a line but a curve. So if this is a Approximated using trapezoidal rule, it would be something like this. We have a line here. In here, it's curved. So this is more accurate because you could see that it's a curve, not a line. So what would be the difference between Simpsons rule and trapezoidal rule? The principle behind is the same. It's just that the divisions here is not anymore in Simpsons rule trapezoids, but rather you have dissections. Okay? The formula, of course, will be changed. But somehow, more or less, quite similar. So the formula for your Simpsons rule is this one. Recall that in trapezoidal rule, the middle terms are multiplied by 2. In here, if you have the drawing, you have 2 divisions. So you have 4 here in the middle. The first and the last terms does not have any multiplier. Your h is still computed in the same manner as you compute it with trapezoidal rule. Upper limit minus lower limit divided by number of divisions. So it's 2. Okay, what about if we have 1, 2, 3, 4? 4. 1, 2, 3, 4. Okay, you have this. So how it's more accurate, of course, than the trapezoidal rule because the ends are curved, not lines. So your formula would be something like this. Now, notice, first and last terms are having no multipliers. They're not having any multipliers. But in the middle, you have an alternate of 4, 2, 4. Which brings about that for Simpsons rule, the number of divisions should be, you have seen it already here, it should be even. So we cannot divide using Simpsons rule by odd number of intervals. We are only allowed to have even intervals because of this. It should be an alternate of 4, 2, 4. The second term and the second to the last term should have multipliers of 4. If you only have 3 terms, the middle term, just like in here, should have 4. If you only have 2. If you have 4, you should have an alternate of 4, 2, 4. So you don't have any division 3, 5, 7, 9. Those odd number of divisions. We don't have that. In Simpsons rule, it's only even divisions. Okay? So first and last terms does not have multiplier. Second and second to the last terms have 4. In the middle, we have 2. So you just alternate 4, 2, 4, 2, 4, 2. It will of course coincide to this particular pattern that the second and the second to the last term will have a multiplier of 4. Now, instead of h over 2 in trapezoidal rule, in here you will have h over 3. H is still b minus a divided by the number of divisions. So in this case, we have 4, so we have divided by 4. Upper limit, the b is x sub 4. The lower limit a is x sub 0. Now in here, if it's in terms of even number of ends, so what about if you have a more general formula for even number of divisions? So that general formula is this one. Okay? Delta x over 3, where delta x is your upper limit minus lower limit divided by the number of divisions. So in trapezoidal rule, you have 2 here. In Simpsons rule, you have now 3. And you have alternates here. Alternate way of multiplying the middle terms between the first and the last by 4 and 2. This is it. Okay? Now, let's see in terms of a specific example. Let's say you have that. Now, this time, the example that I have chosen is not anymore an elementary integral. This is non-elementary already. Because you have here ln of 140,000 divided by the quantity 140,000 minus 2,100t. And you cannot process this expression using the techniques covered in techniques of integration. So the distance covered by a rocket in meters from 8 seconds to 30 seconds. So what would be the distance covered by this rocket? 8 seconds after it was propelled into space and 30 seconds after. So what would be its distance covered? So it's given by this integral. If you're going to use Simpsons rule, so you have here b minus a divided by 6. Let's say using 6 divisions. So it's even. Now you will have, sorry class, this is only 2 divisions rather because there's only 2 terms here. Duha lang 3 terms lang ang dire. So meaning duha lang siya ka-division. So 2, and it's actually based on the formula. Here you have h divided by 3. And this h is actually b minus a divided by 2. I know it's 2 divisions because we only have 3 terms. So 2. So you have now b minus a divided by 6. This 3 and this 2 was multiplied. So you have the 6. Your a is 8. Your b is 30. And a plus b divided by 2 is 19. Okay. Now, what would be the value for this one? So you have f of 8, you have f of 30, and you have f of 19. Now, why f of 8, then 30, then 19? 8 is your lower limit. Okay, this is your lower limit. 30 is your upper limit. The thing in between should be incremented from the lower limit by how much? What's the increment? So the increment, I'm going to use our procedure a while ago. It's the upper limit minus the lower limit divided by the number of divisions. So you have upper limit is 30 minus lower limit, which is 8, divided by 2. So this is 24 divided by 2, and that would be 12. So you're going to increment, 30 minus 8, 24. Divided by 2, you will have 12. So you're going to increment from 8, 12, so this should be 20. Why is this 19? Oh, 8 plus 12, this should be 20. Wait, class. Okay, I'll just clear my markings first. Wait, class, ha? I'll pause recording. Miss Ali is in a hurry to finish. So Miguel pointed out the error, class. So you have our increments are h is 30 minus 8 divided by 2. So this is actually, I wrote 24, it's 22 divided by 2. So that's 11. So this 11 will be the increment to 8 to give it a 19. And then 19 plus 11, that should be 30. Thank you, Miguel. So that's it. And you're going to substitute the value of 8, 19, and 30 where? Where are you going to substitute it? So this is the part that you won't like, especially if the expression is non-elementary, because you're going to go back here on your original integrand and substitute the value of 8, of 19, and 30 to the t, because this is your integrand. This is where you're going to substitute the 8, the 19, and the 30 to get the values of the functions that you have here. So you have, anyway, it's written here already. So you have 177.27, you have 901.67, and you have 484.75. You place it in here. The middle term should have a multiplier of 4. You add. And you will have here 22 divided by 6. B minus A divided by 2 divided by 3. So that would be divided by 6. And this is the distance covered by the rocket in flight. 8 seconds after it was propelled in space and until 30 seconds. So this is Simpsons Rule. Okay? Have any questions? So on a final note, accuracy is dependent on the number of sub-interval chosen. So the greater the number of intervals or sub-intervals, the closer to the exact answer is the value obtained. Do you have any questions?